Welcome to aminacademy.com. In strength of materials, let us discuss about replacing a solid shaft by a hollow shaft, vice versa, some solving problems. Look at this example. Before that, sometimes we are required to replace a solid shaft by a hollow shaft one or vice versa. In such a cases, the torque transmitted by the two shafts should be equal to that by the replaced shaft. We have to assume that. But sometimes there are certain other conditions which have also to be considered while designing the new shaft. Let us discuss for that. Look at this example. A solid steel shaft of 80 mm diameter is to be replaced by a hollow steel shaft of the same material is with internal diameter is 60% of the external diameter. Find the diameters of the hollow shaft and saving in materials. If the maximum allowable shear stress is same for both shafts. Here, solid shaft is replaced by a hollow shaft with same materials, and you have to find internal and external diameter of the hollow shaft. Look at here. First, let diameters of the hollow shaft you are finding. First, D equal external dia of hollow shaft, and small d equal internal diameter of hollow shaft. Which is equal (0.6 d1). That means 60% of the diameter. That is same material is internal diameter is 60% of the external diameter. Now, tau is shear stress developed in both shaft because of same material, and we know that torque transmitted by solid shaft, torque of solid shaft is equal pi by 16 into tau into d cube, which is equal pi by 16 into tau. D is that is given as d equal to 80 mm, 80 cube, and torque transmitted by hollow shaft, that is T1 or hollow shaft TH, you can write T1 is pi by 16 into tau d power 4 minus d power 4 over d1. You can write here d1, which is equal d1 power 4 minus d is 60%, that is 0.6 of d1 power 4 over d1 pi by 16 tau. Since the torque transmitted or and allowable shear stress is same, since torque and shear stress because it's given. Therefore, you have to equate 1 and 2. That is Ts equal T hello, that is 1, which gives, equating both, which is equal pi by 16 pi by 16 tau d cube, that is pi by 16 tau into 80 cube is equal pi by 16 d1 over 4 minus 0.6 d1 for 4 over d1 into pi by 16 into tau, both side, which is cut here, then 80 cube, so we can write the value of 80 cube equal 80 cube here, d1 for 4 minus 0.6144 over d is the calculation is 5, that is 0.8704 d1 for 4. That means here d1 for 4, d1 keep because only cut, means here d1 for 4 taken out, which is 1 minus 0.644 divided by, that is d1, which is given as 0.8704 d1 for cube. Now look at here, that is d1 cube equal 0.8704 80 cube over 0.8704, which is equal to 588,235.3 mm cube. Now taking cubic root, we have d1 equal 83.8 approximate mm. From that, this is the external diameter of the hollow shaft, and internal diameter d equal 0.80 0.83 83.8 into 0.6, 60%, 0.6. Let us calculate this. Here 83.8 into 0.6 equal 50.28. Therefore d, that is equal 50.28. That means that is external diameter of hollow shaft is 83.8 and internal diameter is equal, you can write as 1 decimal 3 mm. Now, next question. Look at here. A hollow steel shaft of 280 mm external diameter and 200 mm internal diameter has to be replaced by a solid alloy shaft, assuming the same areas of polar modulus of for both. Calculate the diameter of the latter, that means the solid shaft, and work out the ratio of their torsional rigidities. Take C for steel as 2.4 C for alloy. Here, first, the external diameter of steel shaft is, first will, that is hollow shaft, external dia of steel shaft, steel, that is solid, hollow, so steel hollow shaft equal, that is D equal to 80 mm, and internal equal, internal diameter equal D, will keep it, equal 200 mm. 200 mm. Next, CS, rigidity modulus, CS is 2.4. Now CS is 2.4 C for alloy. CS is equal to 2.4 C. That means steel, C for steel, and C for steel, and alloy is, write it that one, C for steel is C, and C for alloy is 2.4 times C. Now we'll calculate one by one now. First, we know the polar modulus of hollow shaft. Polar modulus of hollow sail shaft, it is equal, let it be Zs is pi by 16 d power 4 minus d power 4 over d is equal pi by 16, d is 280 power 4 minus 200 power 4 over 280, which gives pi by 16, this calculation 280 power 4 minus 200 power 4 over 280 is equal 16.237 714 into 10 power 6. Now this is a ZS, ZA, that is alloy. Polar modulus of alloy shaft is pi by 16. A solid shaft, it is, let it be D1 power 4. Now equating both, because ZS equal to ZA, polar modulus of solid shaft is equal to polar modulus of alloy shaft, equal, both are equal. Therefore we can write pi by 16, 16.237 23721 into 10 power 6 is equal to 5 by 16 d1 over 4. Here both are equating, then we get 400 will get your dq is at is alloy. That is dq here because it's a solid shaft. Now d1 is taking the cubic root of this, we get 253.2 mm. That means we are replacing that by hollow shaft to solid shaft. Now D1 now here we get the first thing. What is that? Look at here. Here calculate the diameter of the ladder. That means diameter of the solid shaft. Diameter of the solid shaft is 253.2 mm. Next, ratio of torsional rigidities. We know that torsional rigidity of hollow shaft. Torsional rigidity of a hollow shaft is equal torsional rigidity of hollow shaft. This is torsional rigidity of hollow shaft. We are getting CS hollow steel shaft. Z we can keep it. That is CS into JS is equal to 0.4 times C alloy shaft into JS equal y by 32 280 power 4 minus 200 power 4. Similarly, torsional rigidity of a solid alloy shaft is equal CA into JA, which is equal CA into y by 32 is equal to 253. Your 253 point, we got it 253.2 power 4 because we got already the value of the diameter is this one 253.2 that you are using here. Then look at here, the both CA cut, not here, but equating the ratios. Equating the ratios, that is CA, therefore torsional rigidity of halo shaft by torsional rigidity of solid. Here this equal 2.4 CA into pi by 32 into 280 power 4 minus 200 power 4 over 253, that is CA 2 into pi by 32 CA into pi by 32 into 253.2 power 4. Now the calculation now 280 power 4 minus 200 power 4 over 253.244 into 2.4, which gives 2.64 times. That means 2.64 times more. That is, torsional rigidity of halo shaft is 2.64 times more than the torsional rigidity of solid shaft. We have done. Please subscribe our YouTube channel. Here we have to write in first question the maximum allowable shear stress, and same for both, and also saving in material. Yeah, saving in material is the, that means you have to calculate, that is area of cross sections. We can do both, that is area of solid, cross area of the solid shaft. We have 80 mm, the solid shaft have 80 mm, so saving in material, that is pi by 4 into cross area is 80 squared minus pi by 4 50.3 square, that is diameter is 50.3 diameter is 53.3 square, here 83 point, minus your not 50, here 83 point, 83 83.8, higher is outer diameter is 83.8. square minus 5 by 4, that is internal is 50.3 square over outer is 5 by 4, 80 square. Here 5 by 4 take out and cut, the remaining things is 80 square minus 83.8 square minus 50.3 square over 80 square. Now I calculate this. First 80 square got 6,400 minus, here the calculate is 83.8 square minus 50.3, 50.3 square equal 4492.35 over 6400 into 100%, which is equal 6400 minus 92.35 is equal 1907.65 over 6400 into 100, 1907.65 over 6400 into 100. That is 29.8%. 29.8% of saving material by replacing a solid shaft to hollow shaft of this condition. Here, that is saving in material of the shaft by replacing a solid shaft to hollow shaft. We have done. Please subscribe our YouTube channel.